this is our project 2 for Physics 211, and we chose to do the second problem. And in this problem, we have two masses, one mass B and one mass R. And mass B is initially compressing a spring some distance xi, and mass R is initially at rest. So we move from the spring being compressed by MB into the spring pushing mass B off, and it travels along a frictionless surface until it comes into contact with mass R. And then at the moment that they hit each other, they collide and stick together, and then mass R and mass B slide together, combined on some friction surface. They travel some distance x. And so our ultimate goal is to find that some distance x that they traveled together after their collision.
Alright, this is our little mini demo. We didn't have the exact material we needed, but we use these two cars as our different masses. So we have the red car and then the blue car, and then we didn't have a spring, but we used the spring, which has like elasticity and a spring constant, just like other springs would do. So we just kind of catapult it. And this area over here is our frictionless surface, and then over here with the paper is where the friction is actually added to the problem. Alright, so in this project, looking at the first instance, we can see that the first box, MB, is put next to the spring. And so for our system, we chose both masses of the boxes and the earth, because we know that this distance that MB moves is frictionless. So the friction has no effect on the box at all, just the gravity and the mass. So then we know that the external total work force is going to be equal to the force of the spring pushing on MB. And then we know that the total change in energy is going to be equal to the force of the spring. Before the spring actually pushes MB, we know that the total energy is the potential energy, and then when the spring actually pushes the box and it now has a velocity, we know that the potential gets converted into kinetic energy. Therefore, we can say that kinetic energy equals the force of the spring. And then we can write this out mathematically, saying that kinetic energy equals the force of the spring, and by isolating the velocity, we can solve for it, and we're given root k over mass b times the displacement of I.
So at the instant both the boxes collide, we're assuming that the time takes for it to collide is equal to 0. So plugging it into the equation of impulse, we know that the impulse is 0, the momentum is conserved. So the initial momentum will be equal to the final momentum. The initial momentum would be of both the boxes individually, and then the final momentum would be of the entire system of both the masses. And we know that the red mass is at rest initially, so the overall momentum of it would be 0. And plugging in the velocity from the earlier equation, we get the overall velocity of the system to be this number.
So the final step to this problem is the section where it travels along a friction surface, and we're trying to find some distance x that hauls it to a stop. So we know that on this friction surface it has to be kinetic friction because their boxes are moving, and so kinetic friction equals the coefficient of friction times the normal force. And if we draw up a free body diagram like we have here, we can see that the two forces acting on the boxes at this time are a normal force and a force of gravity, because it's no longer in contact with the spring. So our normal force must equal the force of gravity, which equals mass times g. So we plug that in over here. We know that kinetic energy is what is pushing these boxes forward, and we know that over some distance x it hauls to a stop because of kinetic friction. So our kinetic friction must equal mu sub k mg times some distance x. And if we set the kinetic energy equal to the kinetic friction over some distance x, we can see that when we plug in our masses of the system and then our velocity, which we have here, squared, and that is equal to our kinetic friction times some distance x, and then we're gonna isolate x here, and then we're gonna solve for x, and what we end up with x equals k times mb times xi squared divided by the mass of the system times gravity times the friction coefficient. So this is our solution for the problem where the system has slid some distance x. And so we're going to do some sense making with this, and we're going to start with a unit check. So K is our spring constant, and spring constant has units of newtons per meter. And then this is a mass, so we have units of kilograms here. And then xi is the initial distance the spring is compressed, so that's going to be a displacement. So that's in meters squared, and that's all over. These are both masses, so it's going to be kilograms, and that's squared. And then we have gravity, which is m over s squared. It's an acceleration, and then our coefficient of friction is unitless. So initially we can do some cross canceling here with the kilogram and one of our meters. So we're left with newtons times meters over kilograms times meters per second squared. And a kilogram meter per second squared is equal to a newton. So we can cross cancel these. So what we're left with is meters, and that's what we want because our answer should be a displacement x, so meters will equal meters, which is perfect.
For more sense making, we're going to be looking at each variable, and we're going to be imagining if we change them either larger or smaller and see how that would affect the distance. So for now we can look at the gravity, and if we were on a different planet, let's say, and the gravity was less, then we would get a larger distance because gravity is on the denominator, so that would give us a larger distance. And then also this would be the same with the spring constant, the coefficient of friction, sorry. And if this were to be larger, then the distance would be less because it has to, the kinetic friction would just be more, so it would travel less.
And so if we use a more rigid spring, it would push it further apart or more away. So if we increase the spring constant, with the numerical answer, we'd also get a larger distance. And so is it with the initial distance. If we use a more rigid spring, it would be compressed even further away. So overall would increase the distance.
And so looking at the masses, if we were to increase mass B, this one's a little tricky because it's on the numerator and denominator. So it would make it go a little bit faster because the larger mass would shoot a little more off the spring. But then when it travels and runs into friction, it's going to slow it down a lot more with a heavier mass. So ultimately the larger mass is going to slow it down a little bit because it's squared on the bottom down here. And then if we look at the mass of R, so the red mass, that's on the bottom of the fraction. And so we know that if it's larger, it's going to slow down the distance x. We're not going to travel as far. And this makes sense because if mass R is larger, that means that when mass B hits it, it's going to slow it down a lot more. And the friction that it's going through to travel some distance x is also going to slow it down more.
And then for our final reflection, we just looked through some problems that would have been similar to this problem and or different. And so one problem that I found was my final lab. I worked on the elasticity of springs and of rubber bands and looked at their coefficients and see if those made a difference. And what I noticed is that as mass was increased or decreased, the spring force would increase proportionally with that as well, and it would have a linear pattern. And that makes sense here, because if we were to increase masses of both of these, our distance probably wouldn't be as much compared to if we used a smaller mass. So that's what I thought was similar.
And one of the similarities and differences in the question would be the homework question we did a couple of weeks ago was the potential energy question of the apple that was attached to a spring and was falling from a tree. In that question, we were finding the distance the spring was compressed and elongated when we dropped the apple with the changing masses. And over here, we do have the spring which is pushing the box, but it only pushes the box, and we're trying to find the distance that the box slides after it collides with the other mass. Unlike the homework question where we found how much the spring was being compressed and elongated.
So the problem that I thought about was the one from the studio, and this one reminds me a little bit of it because it deals with a mass and a spring. But in the studio problem, this mass was actually attached to the spring, and so that was a lot different because it was dealing with elongating the spring, so pulling it back, and then releasing the mass and seeing how much the spring compressed. So that was a little bit different. And then finally, we thought about how this problem was really good at sort of summing up our term because we felt it dealt a little bit with each of the three main sections that we covered. So motion, initially, we didn't have a lot of equations that dealt with motion in this problem, but just we had to think logically about what would happen to each of these things due to each of the variables that was going on. And so that dealt with a little bit of motion. And then the forces in this problem was another section that we went over a lot of. And that we had to do a lot of equations with forces and different things going on and different things acting on this problem. And then finally our energy and unit was the last one that was the big one that we dealt with. And this problem had a lot to do with energy and conservation of energy and the change in energy. So we felt it was really good at summing up our term.